All right, good morning, everybody. So picking up from where we left off in the last lecture, we were talking about lists. Right? So just to remind you, these are some of the basic list operations that you can perform. Right? So where's the Python? Here we go. So if you like Python lists, then this might be the easiest way to figure out how to use a Java list. Right? So, yes, question?
There are many ways to, I think there are different ways to use the array list. What's the difference? There's the difference between this array list, what I'm looking at, and the other one is the string inside again.
The difference between an array list and what?
You mean the formula? The Python, the first one, Java. Why does Java is the array list string equals new array list square bracket, but is the string if you write string in both square brackets? Do you think about writing the string in both square brackets?
Yeah, so you can put the type in both sides if you want to, but there's no difference.
Oh, can I do that?
This is shorter to write. Okay, so just to quickly remind you, right? So if you're used to working with Python lists, then this table is handy. So can you please stop talking, especially if you're in the front row? All right, sorry. So again, could you please stop talking? I can hear everything in the room. Okay. So if you're used to Python lists, then the left-hand, using this table here, it's relatively easy to translate to a Java list. Right? Also remember that lists are not the same as arrays. Right? So with lists, you're never using square brackets. Right? The only place you can use square brackets in Java is when you're using an array. The other difference between a Java list and a Java array, right? When you go to get the size of the list, so the number of elements in the list, the method is called size. It's not length. Right? Add always adds to the end of the list. Now don't get that confused with set. Right? So set replaces an existing element in the list. Right? If the element doesn't exist at this index, right, then you end up with an error. Right? So there has to be something already in the list at that index before you use set. Right? Set should really be called replace or something like that. I think generally programmers tend to choose short names for their methods, especially ones that are used very often, because it's easier to write the shorter methods. Sublist. So we're going to see a lot of sublist later in this lecture. So remember, sublist is the method that returns part of a list back to the caller. If you want to copy a list, then the easiest way to do it in Java is just to call a constructor. So if you'd like to copy the list t, then just make a new array list and pass in t as the argument. That will make a new copy of the list, which you can then use. So u would be a reference to the new list. Right. Now remember, when you do this, the elements in u, they are the exact same elements that are in t. Right? So for example, if you were to take one of the elements in t and call a method on it that changes it, the corresponding element in u will also change. Sorry, what's going on with the volume today? All right. Another one of the big differences between Java and Python is that a lot of the methods that you would think would be part of the list class are not part of the list class. So for example, if you want to count the number of times something appears in a list, you have to use a second class to help you do that. Right? If you want to reverse a list, you have to use a second class to help you do that. Right? Sorting a list, you have a choice here. Question, yes?
So then why did when you use Java? They say you just have why do they use frequency?
That's the way it was designed.
I get it. I think this happens.
All right, so if you want to iterate over a list, then it's pretty much the same as iterating over an array. The main difference, again, is that you're not using square brackets to get to the elements. So this method here finds given a list t, it finds the shortest string in the list. Right, so what you're going to do is you're going to look at every element in the list. You're going to get the length of that element. Right, you're going to remember what the shortest element is that you've seen so far. Right, so assuming you have a non-empty list, you can always get the first element. You're going to remember what its length is, right? And then you're going to iterate over the rest of the elements in the list. So here you can use a for each loop. because I only need to look at one element of the list at a time. Right? Now you might have noticed that in that for each loop, you're going to reprocess the first string, which we did here. Right? So if you're using a for each loop here, you're going to look at the first string twice, right? Even though you don't have to look at the first string twice. But that's fine for this particular problem. Right? You could also use a counting style loop. Right? So remember, a list is an indexed sequence. So using a counting style loop, you could write the same piece of code like this. Right? Now, if you use a counting style loop, you can start at index 1, so you can avoid looking at the second element twice. Right? Of course, the problem with the counting style loop is that now you have to get the element yourself each time. Right? In the for each loop, the for each loop takes care of extracting the element for you. Right? So the compiler is actually converting this for each loop into something that actually asks the list for its element. Right? Here, you have to explicitly ask the list for its element yourself. Right? So every time you're going to call get, right, to get the ith element of the list. Yes, question?
The other method, did you think about the other method in other slides?
This one?
Yeah, did you think about the other method in the for loop?
Did I think of it? I don't understand what your question is.
I mean, I'm talking about, does the other method work? Like n s equals to n greater than.
So these are almost exactly the same. The only difference is that you're using a counting style loop here, and you're using a for each loop here. The only difference. Yes?
So I just double checking. When we're using this array list object, I'm assuming that when we use the method like get, specific item in that place, it's going to be a lot slower than using a regular array.
No. So they have almost virtually this. So they're almost exactly the same speed. There is almost no penalty using a list as opposed to using an array. Yeah. In terms of performance, there's almost no penalty. Later in the course, we're actually going to implement an array list, and you'll see exactly what's going on. All right. Okay, so there is a small issue with the code with those two, the two versions of the code from the previous two slides. If you're frequently looking for the shortest string in a list, then you should probably write a method to do so. And so here I've got a method called shortest. It takes in an array list as its parameter. It takes in an array list as an argument. Now, if you're taking in an array list from somebody else, you don't know if there's anything in that list. So you have to deal with a situation where the list might be empty. Notice that in the code from the previous two slides, right, the first thing we do is we get the first element out of the list. Right? That causes an error if the list is empty. Right? And that's why up here it says this works for a non-empty list. So to deal with a case where the list might be empty, you should check, right? Is the list empty or not? And that's where you would use the isEmpty method. You could also use size and check if the size is equal to 0. But isEmpty is probably a little bit easier in this case. Right? If the list is empty, there is no shortest string. And so you have to decide what is it you're going to return back to the caller. Right? In this case, I've chosen to throw an exception. Right? But you might choose to do something else. Right? So for example, you might choose to return null to indicate that there is no object that is the shortest string in the list. Right? You might choose to return the empty string to indicate that the shortest string has length 0. Right? It's up to, so this is a decision that you'll have to make if you're designing these kinds of methods. Right? I think here, arguably the correct thing to do, I think, is to throw an exception. The rest of the code is exactly the same as from the previous two slides. Okay, so here's another example of using a list to solve, I guess, a sort of interesting problem. So here we're going to use a list, and we're going to try to solve the problem of calculating the odds of rolling 2 dice, right? So what is the odds of rolling a 2 through 12 if you're rolling a pair of dice? Okay. I guess you might have taken some sort of probability or stats course in high school. You might have taken one in university. If you've done that, you almost certainly know how to calculate the odds here, right? If you don't, then I guess the things to notice here are the highest probability of rolling a value is rolling a 7, right? Rolling a 6 has the same probability as rolling an 8, right? Rolling a 5 has the same probability of rolling a 9, and so on and so on and so forth. So this is a symmetric distribution of probabilities, right? It sort of looks like a bell curve. So if you don't know how to calculate these values, or if you don't know how to calculate these values analytically, you can solve this using a computer, right? The idea is you just simulate rolling 2 dice over and over and over again, count the number of times that you rolled a 2, a 3, a 4, and so on and so on and so forth, right? And that would produce, hopefully that produces something that resembles that table right there. All right, so if you want to roll 2 dice, you need some way to generate a random number. So I'm going to use the random class to do that, right? You saw the random class in assignment 1, right? You also use the next int method in assignment 1, right? So you should be familiar with this class by now. So I'm going to generate a random number between 1 and 6 twice, add it together, and that'll give us our simulated dice roll. All right, so the steps you want to take. So basically, I want to reproduce this table here, right? And so on the left-hand side, you've got something that looks like an index, and that's exactly what I'm going to do. Right? On the right-hand side, you've got something that looks like a value. So I'm going to make a list that starts, that has 13 elements in it. Yes. So this is, no, if you have a pair of fair dice, then that is the correct, that is the theoretically correct probability. Okay, so I'm going to make a table. Sorry, I'm just going to use a list. The index of the list is going to correspond to the value, right? So the element at index 2, hopefully, when I'm done, I'm going to have something that looks like 2.78, right? The element at index 3 is going to look, hopefully when I'm done, it's going to look something like that, and so on and so on and so forth. The elements at index 0 and 1, they should just be 0, so we're not going to use those at all. So I want to make a list of size 13, right? And I want to add 13 zeros to the list, right? And then, because I'm going to count the number of times that I roll a 2, a 3, and so on and so forth, right? So the zeros are going to represent the current count, right? I'm just going to write a loop that runs n times, where n is some large-ish value, right? I'm going to simulate rolling 2 dice. So suppose I get a 6. I'm going to go into the list and look at what's stored at element 6. Right? I'm going to add 1 to that value and put it back into the list at index 6. Right? That'll give me the number of counts, right? So the number of times that we saw each value. If you want to compute the probabilities, you just divide everything by the number of times that you rolled the dice. Right? And so you can easily do this in Eclipse. It's not very long. And so let's do this. Okay, so let me get rid of this. Oh wait, that was the dice example. Okay, so I'm just going to write a little main method. Inside the main method, we're going to make a list. I guess I should call that count instead of t. Right. I want to add 13 zeros to the list, so I want a little loop. And now I want to add a 0 to the list each time in the loop. So you just write count and then add and 0. Oops, sorry, 0. Right? Add 13 zeros to the list, and there's your list. Right? If you want, you can print out. Oops, sorry, you can print out the list here just to make sure that we actually have the correct list. Right? And if you run that, right, that's the output that you get when you print a list. Right? So lists know how to print themselves. So when you call this print line, when you call print here and pass in the list, you end up getting something that looks like this. So it always starts and ends with these square brackets. Each element of the list gets converted to a string, and then you get a comma and a space between each element. Right? So this works for any list. Yes? How do we know there's 13 elements in the list?
Well, no. Or you can write it's size. Array list is size. I just the right one.
can I print the size of the list? If I want to, but I mean, if you want to print its size, you just call size. Right? That's going to be 12, or 13, sorry. Okay, so next step, we want to repeatedly roll 2 dice n times. So pick a value for n. So I'm going to use 100. Right, write a loop. Right, inside the loop, I'd like to roll or simulate rolling a pair of dice. Right, so I guess the easiest way to do this is to use a random object. Now I could make the random object here. Right, and then I can just call RNG next int twice to get some integer values. Right? Now the problem with this is that every time through the loop, you're going to make a new random object. Right? And I don't need a new random object every time. Right? I only need one random object. I can just ask that one random object to give me back a random value over and over and over again. So it doesn't make sense to create the object in the loop. Right? It would be better to put it before the loop, like that. Right? And now I just want to simulate rolling the dice twice. So I'm just going to call the 2 dice x and y. Okay, so when you call next int, if you have the 1 argument version, it produces a value between 0 and, in this case, n minus 1. I would like a value between 1 and 6. Right? So what I'm going to do is I'm going to generate a value between 0 and 5, and then add 1 to it. Right? And so to get a value between 0 and 5, you would write next int 6. Right? So the 6 is the upper bound of the range, right? But the range never includes the upper bound. Right? I guess interval is the better word for it. Right? And so that will generate a random number between 0 and 5. Right? To get a number between 1 and 6, just add 1 to the result. And that gives you 1 roll. Right? Do the same thing. That gives you the second roll. Right? Sum the values. Right? Okay, so that gives me, I don't know, say it gives me 8. Right? I now want to go into the list and look up how many times has 8 occurred. Right? So int, I guess we'll just call it cur. So for the current count. Right? So my list is called count. I want to get the value at the sum. Right? I now want to add 1 to that count because we just rolled another value equal to cur. Right? Sorry, equal to sum. We just rolled another value equal to sum. Right? And then I want to put it back into the list at index sum. Right? So to put it back into the list, right, it's set. The index is going to be sum. Right? The value is going to be cur plus 1. Like that. Right? And so we're going to count the number of times that you've rolled that value. Right? So when we're done, hopefully we've got a list that has some numbers in it that are not all 0. Right? So if you're debugging this and you have no idea what to expect, right, you have to approach this analytically. So you approach this logically. Right? I'm going to roll the dice 100 times. So there should be no value in the list that's bigger than 100. Right? The first 2 values at 0 and 1, they should be 0. Right? If the table that I showed you previously is correct, then you're going to expect you're going to expect the value at index, whose index is 7 to be the largest in the list. Right? So let's see what we get. Right? And so we get that thing there. Right? So the first 2 values are in fact 0, so that's good. Right? The number of times that we rolled a 2 is 4, so 4 out of the 100 times. Right? We saw a 12, 0 out of the 100 times. Right? The largest value, so interestingly enough, it's not 7, I don't think. So 2, 3, 4, 5, 6, 7. Right? So it looks like we rolled a 7 15 times, but we actually rolled an 8 more times than the 7. Right? And so this doesn't exactly match, or the pattern is not the pattern is not exactly the same as the values or of the pattern of values in this table. Right? But that's because everything we're doing is random, right? And so if you repeat the process a larger number of times, right, the values here, the pattern in this set of values will start to approach the pattern of the set of values that I showed you in the table, right? And if you want to see this more clearly, we can print out the values in a slightly nicer way, right? So I'm going to print out the values one line at a time. Each time I print out a value, I'm going to divide it by the number of times by n, right? So now I'm going to use a for each loop, right? So when you're using the for each loop, what is the element type of the array? Well, the element type is integer, right? So in the round brackets for each integer, I don't know, c in count, right? I would like to print out the count. I'd like to print out c, and then I would like to print out, I'd like to print out c divided by n. And it would be nice if I actually printed out, well, let's print out c divided by n. C divided by n, like that. Okay, let's see what we get here. Let me make this a little bigger, because we're going to get 13 rows out now. Okay, you run that. What do you get? We get all zeros. You say, well, that's weird. Why am I getting all zeros, right? Why am I getting all zeros? Anybody? Yeah?
Because they're integers and they're just rounding down to 0.
That's exactly right, right? So c is an int, or an integer, right? N is an int. So when Java sees int divided by int, it says, okay, we're doing int arithmetic, right? All the values in the list are smaller than n. So you get some value divided by some larger value. In integer arithmetic, that always produces 0, right? So what's the solution? I have to do this in double. So I have to force one of the two arguments to be a double value. So I can add 0.0 to either one of the values, or I can just cast one of the two values to double. So I'm going to choose the cast because it's slightly easier to write in this case. Oops, sorry, like that. All right, now let's see what we get. Okay, better. We can do slightly better. We can multiply it by 100 so that we don't have to do the division ourselves in our head. And voila. So there we go. 2.3, 4.4, 8.3, 11.6, and so on, and so on, and so on. Right? Compare that to the table. Right? So it's 2.8, 5.6, 8. And so on, and so on, and so on. Right? And you might say, well, it's still not exactly the same as the table. And again, the answer is, well, yeah, it's random. Right? So increase the number more. Let's do 1 million. See what we get. Right? Now we're getting much closer, right? So 2.8, 5.5, 8.3, and if you go the other way, right, 2.8, 5.5, 8.3, right? So it really is, if you increase n to infinity, so if you run this forever, you will in fact, assuming the random number generator is fair, you will in fact converge to these values here, right? And so that's just a little example of writing a very simple simulation, using a list to store the values, or to help us store the values, using the random class to generate some random numbers, right? Doing some basic arithmetic here. Yeah, so that's the rolling the dice example there. Any questions? So in the slides, there's another simulation. Oh, sorry. In the next set of slides, there's another simulation. So this is the list part 2, so the second set of list slides. Yeah, question?
Actually, sorry, if we go back to the code, I was just wondering.
Back to the code? Yeah, here.
On the count.set,
Yeah.
can we technically not, can we just use instead of code plus 1 count.getSum plus 1? Like, can we use the method inside the other method?
Yeah. So the question is instead of making this variable cur, right, or instead of using this variable cur, can I not just write count.getSum, right? And the answer is yes.
Is that preferred? Because it's like a variable.
Is this preferred? Is this preferred? I would say no, it's not preferred. If you're worried about creating a variable and using extra memory, I mean, it's just an int. Like, if you're in the situation where making one int is going to cause problems, you have other problems, right? So, and I guess, I suppose, at some point, if you ever take, what would you have to take to do this? So I guess the real answer to your question is what is the computer actually doing when you write down code like that? And you won't know the answer to that until you take some course where you learn about assembly language. So, yeah. So I think when you get to that point, you'll realize that there really is no difference here. Yeah. Yes? Yep. So if you do a bound of 7, you get a number between 0 and 6. You don't want to roll 0. Right? The lower bound is always 0 if for the one argument version of nextInt. Yeah. Any other questions? All right. Deck 2. Where's Deck 2? This is not Deck 2. Lists 2? Oh, sorry. Okay, you can do the exact same thing, or something very similar, if you want to simulate flipping a coin. Right? So if you're interested in the answer of, if I flip a coin n times, what are the odds that I see 0 heads, right? Or what are the odds that I see n over 2 heads, or whatever you want. You can do the exact same, you can do something that's very similar, right? So you can make if you want to enumerate what all of these probabilities are, right? You can make a list that has n plus 1 elements in it, right? Set them all to 0, simulate flipping a coin a whole bunch of times, and then count the number of times you see 0 heads, 1 head, 2 head, and so on and so on and so forth. Right? Again, if you've taken some statistics already, you know this is the binomial distribution. Right? So there's the description of the algorithm that you might use to simulate flipping a coin n times and computing the probabilities that you would see 0, 1, 2, 3, 4 up to n heads. Right? It's almost exactly the same thing. It's now you have a nested loop. Right? So you need a nested loop because this part here simulates this loop here simulates flipping the coin n times. You want to do this many, many times. So you're going to put that in an external loop out here. Right? So you just have a nested loop now. Instead of solving the problem in Eclipse, I'm just going to give you the solution here. Right? So if you want to, you can type that in, play around with that, and see what you get. Right? Again, as you increase the number of times that you run the experiment, so that's m in this case, you'll get results that are closer and closer and closer to the true odds. If you look at this slide here, so if you look at the code here, you'll see that there's two variables here that are marked final. We haven't seen that before. So if you mark a variable as being final, what that means in Java is that you can only give it a value once. You don't have to give it a value where you declare the variable. But when you do give it a value, you're only allowed to assign it once. So here, final int big N equals 20, right? Means that the value of n can no longer change, right? I've set it to 20 once, can't set it to anything else because it's marked final. Right? So later on, if you wrote big N equals 5, the compiler would say you're trying to change the value of a final variable. Illegal, right? It won't compile your code. Here we've got a final variable m, so the number of times that we're going to repeat this simulation. Right? And so these are marked final because I don't want to accidentally change these values somewhere else, because accidentally changing those values will invalidate the results of the simulation. Right? So I've made them constants here. And we're going to talk more about creating constant values later in the course. When you make a constant value, you can break the rule where the variable names always start with a lowercase letter. Right? The exception to that rule is when you make a constant. Right? If you make a constant, then typically the constant name is spelled out in all caps. Right? So here we have n, here we have big M. Right? In the integer class, you've got max value and min value, right, in all caps. Those are just constant fields in those cases that are in the integer class itself. Okay, so 120, you do, right? Okay, this is the recursion lecture in this course. So we're going to do recursion on lists. Possibly covered on the exam, sure, or the quiz. I don't usually ask you about it, but it could be. So the situation, so I'm trying to solve the following problem. You've got this not very exciting game called Jump It, right? So the game is just a linear board, right? You have a number in each square, right? The first square, oh no, that's not true. You have a number in each square, it's always a positive or 0, right? The number in the square is equal to the cost of stepping on that square, right? So first square has cost of 0, second square has cost of 3, last square has a cost of 10, right? You would like to start from the left-hand side of the board and make it to the right-hand side of the board, accumulating the lowest cost, right? So minimizing your score, I guess, in this particular case. When you move, you're allowed to move 1 square to the right, or you can move 2 squares to the right. Right? So every step you make is always 1 or 2 steps to the right. Okay? All right, so for this particular board, what is the lowest cost solution? Well, I start at the 0, so I'm going to go to the 3, right? Because my choice is between 3 or 80, right? So the sensible thing would be to move to the 3, right? 3 is less than 80 after all. Right. Now when I get to the 3, my choices are between the 80 and the 6. So again, it looks like the sensible thing to do is to move to the 6. Right? And now 57 and 10, well the 10 is much smaller than 57. Also the 10 is the last square on the board, so it looks like that's the right move to make. Right? So for this particular board, you can quickly convince yourself that the correct solution is to move 1 square, then 2 squares, then 2 squares. Right? For a total cost of 919. And so to generate that solution, what I did was I always picked the move that resulted in the lowest cost, right? And so the question is do you always generate the lowest cost solution by doing this, right? By always picking the next square with the lowest cost, right? And the answer is no, that doesn't work, right? So if this worked, right? If that worked, this is easy to solve with just 1 for loop, or 1 while loop, or something like that, right? So basically your loop says, until you reach the end of the board, right, pick the move with the next lowest cost. That's easy to write. Turns out it doesn't work, right? The reason it doesn't work is because moving to the square with the next lowest cost instead of moving to the square to the lowest cost, you might be able to avoid that square altogether because you would have ended up on the same square in either case. So here's the strategy by where you move to the square with the next lowest cost. Right? So starting at the 17, right? My choice is between the 1 and the 5, so I'm going to move to the 1. Right? Now my choice is between the 5 or the 6, so I'm going to move to the 5. And now it's between 6 and 1, so now I move to the 1. Right? Stepping on the square with the 1 is suboptimal because you could have just jumped to the 5 directly. Right? So picking the square with the next lowest cost isn't guaranteed to work. Right? And so if that strategy isn't guaranteed to work, you now have to come up with a different solution to this problem. Right? And if you try to come up with a solution to this problem using just 1 for loop or 1 while loop or something like that, right, it's not at all obvious what that solution would look like. Right? Okay, so instead, I'm going to attempt a recursive solution for this problem. Now remember what you need to solve a problem recursively. Right? And so if you're going to write a recursive method, there are some conditions that must be true before you attempt to write the solution. Right? So one of the conditions is that when you're using a recursive solution, right, every time you recurse, right, you're trying to solve a smaller version of the original problem. Right? If you recur and then you're trying to you solve a larger version of the problem, right, there's no guarantee that the recursion ever stops. Right? Because when you recur again, you might end up solving a larger version of the problem, and then so on and so on and so on. So the problem size must always decrease if you're attempting to find a recursive solution. Right? Also remember that in a recursive solution, you need some cases where the recursion can stop. Right? Those are called your base cases. Right? And when you're trying to solve a recursive problem, right, it's always useful to draw out some simple problems or some simple little examples to help you find your base cases and or recursive cases. Right? If I had a blackboard here, I would, oh wait, we have a whiteboard. Do we have a whiteboard marker? Are there any markers up there? There are not. Okay, so I guess you're going to have to imagine this in your head. So let's try to sketch out some small versions of the problem, right? So the smallest version of the problem is the board of size 2, right? That has an easy and obvious solution. You just step 1 square to the right and you're done, right? So if you reach a board of size 2, you're done. You've got one of your base cases, right? You know the answer. Similarly, if you have a board of size 3, right, you know that you can skip the middle square and just jump to the last square, right? So now you're also done. So that's nice, right? Now you get to a board of size 4, right? And this is where you have to make a decision now, right? So in a board of size 4, right, you can either step to the first square, right? And when you step to the first square, you're left with a board of size 3. So I know the answer there, right? Or you can step to the square, you can step 2 squares to the right, and that leaves you with a board of size 2. So we also know the answer there, right? So if you really wanted to, you could write a base case for a board when the size, for a board of size 4, right? But you don't need to, right? So if you go back and think about what you just reasoned out, right, you'll realize that when you have a board of size 4, that leads you immediately to the recursive solution, right? Either I take 1 square to the right and then solve the rest of the board, right? Or I take 2 squares I step 2 squares to the right and I solve the rest of the board, right? The solve the rest of the board part is the recursive call, right? So here are our base cases. The board has size 2, you just move 1 square, right? Your total cost is the cost of the square that you're on plus the cost of the final square, right? If your board size is size 3, just move 2 squares to the right and you're done. So your total cost is the current square that you're on plus the cost of the last square, right? And so now you just write down your base cases in your method, right? So I'm going to write the method called cost, right? It returns the cost of solving that board, right? So that's how our method's going to work, right? So if the board size is 2, we know the total cost, right? It's just the sum of the elements in the board. Right? If the board has size 3, we also know the total cost, right? It's the sum of the first square plus the cost of the last square. And now here, we're going to have our recursive cases, right? So in the recursive case, you're going to move 1 square to the right, right? When you move that 1 square, that's going to incur a cost, right? You're also going to consider moving 2 squares to the right. That also incurs a cost, right? After moving 1 square, you're going to solve the remainder of the board, right? After moving 2 squares, you're going to solve the remainder of the board, right? The smallest cost of solving the entire board is whichever one of these two is smaller, right? So now you have the problem of, well, how do I get the rest of the board, right? So to get the rest of the board, right, so if I take 1 square to the right, the rest of the board is the original board minus or not including the first element, right? That's what the sublist method is for, right? So the sublist method gives you the part of the board starting at that index, going up to but not including that index, right? So sublist 1, comma, board size gives you the list that consists of the original board, not including the first element. Right? If you go 2 steps to the right, you don't want the first or second element of the board. So again, I can call sublist, right? Starting at index 2, going up to but not including the size of the board, right? And that gives you the board not including the first 2 elements of the board. Now the way that sublist works is that the list that's returned by all of that is actually part of that list, right? So it really is a sublist of board, right? If you modify the sublist, you modify the original board. If you modify the original board, you also modify the sublists. Okay, so now that I've got my boards after taking one step and after taking two steps, right? I can solve for the cost of those boards by recursively calling the method, right? So I'm going to compute the cost after taking one step, and I'm going to compute the cost after taking two steps, right? I would like to know what is the smaller of those two, right? Math.min will tell you the smaller of two values, right? What is the total cost? Well, it's the cost of the square that I'm currently on, right? So that's the cost of the square at index 0, right? Now remember, that's not the first square on the entire board, right? When I recursively call cost, right, I'm passing in a sublist of the original board, right? The starting element of the sublist is index 0. So the current square that you're on is always at index 0 in this method, right? So C plus the smaller of the two costs gives you the smallest cost for solving this board, right? And that's your recursive method for solving this problem. All right, any questions? Super. All right, so you might say, well, okay, you've got the smallest cost. Can you tell me the sequence of steps that you would need to get the smallest cost? The answer is you can, right? I'm not going to do it for you, though, right? So if you want to solve this problem here, right? So for example, I would like to know that I'd like to know two things. I'd like to know that the smallest cost is 19. I would also like to know that the sequence of moves is 1, 2, and 2, right? So I'd like to be able to generate that list as well, right? And so if you want to solve this problem, I suggest attempting to write that method right there, right? So in this version of the method, it's the same thing. It's called cost. You pass in a board. The first time you call the method to solve an entire board, you pass in an empty list, right? So an empty list of moves. And your cost method should fill in that list with the sequence of moves that are made, right? Also returning the total cost of solving the board, right? So if you're interested in practicing recursion, give that a shot right there. Okay, so that particular version of the game has a couple of nice properties, right? So you're always moving to the right, and so that it's obvious that the board is getting smaller and smaller and smaller, right? And that is one of the things that you're looking for when you're formulating a recursive solution. Also, the rules of the game, they don't let you land on the same square twice, right? And that's also nice, right? So that's a nice feature. And finally, it's impossible to move off the board, right? So there's no way that you can jump off the left or right-hand side of the board. And so that's also nice. What happens if you remove these two constraints, right? Okay, so similar game now. I'm going to start at the left-hand side of the board. I want to get to the right-hand side of the board. The right-hand side of the board always has a 0 in it, and it's the only square that has a 0 in it. Everything else has a positive value. Right. The number in the board is not the cost. It's the number of squares left or right that you can move. Right? You're not allowed to move off the board. So starting at the 2, I can't move left, so I can move 2 squares to the right. Right? So I can go to the 4. Right? If I get to the 4, I'm not allowed to move 4 squares left, but I can move 4 squares to the right. Right? I'd like to try to get to the 0 at the end. Right? So this is a solution sketched out. Right? Starting at the 2, I have no choice. I must move 2 squares to the right to get to the 4. Right? On the 4, I have no choice. I must go to the right to the 1. Now I have a choice. Right? We can go to the 6 or the 2. So I'm going to try the 6 and see what happens. Right? Can't move 6 squares right, so I must move 6 squares to the left. Right? Can't move 3 squares to the left, so I must move 3 squares to the right. Right? When you land on the 5, you say, oh, I get to the 0, and there's a solution. Right? This particular board has many solutions. Right? So solution number 2, go right 2 squares, go right 4 squares. Right? Now go left 1 square to get to the 2. Right? Now remember, once you get to this 2, we know that there's a solution by going to the 6. So if you just jump to the 6, you know that you can solve this board. What if we go to the 2 instead? Right, so I'm going to go to the 2. Now when you get to the 2, right, I can go to the 3 or the 2. Right? It doesn't seem to make sense to go back to the 2. Right? That doesn't seem to be making any progress. So I'm going to go to the 3. Now I have to go to the 5, and now we know we have a solution. Okay, so on this particular board, there's a cycle, or there's at least one potential cycle. Right? So a cycle occurs when you start at a square, you make some sequence of moves, and you end up back at the same square. Right? And so this has an obvious cycle. Right? I can just keep on going around and around and around, stepping on one of the two 2s every time. Right? So if I'm trying to write a solution to this method, to this problem, I need to be able to detect that the solution I'm currently considering is in a cycle, right? And I want to reject that solution, right? So I want to avoid going in cycles, right? If you have cycles, you can easily make a board that has no solution, right? So that board is impossible to solve. You just end up going from the 2 to the 2 to the 2 every time. When you're trying to solve the problem, you would like to know this board is not solvable, right? And on that board there, it doesn't matter what sequence of moves you make, right? You eventually end up on the 1, right? Once you land on the 1, that forces you into a cycle of some kind, right? So as soon as you land on that 1, you end up on that 2. You can only go to that 2 or that 2, right? And you end up, you can end up going around and around in circles. You don't even need cycles to create a board where there's no solution, right? Here, you have to go to the 100. Once you land on the 100, you're stuck. You can't go anywhere, right? So you would like to know that board is also not solvable. Right. Now, this particular version of the problem, it doesn't look like the board gets smaller every time, right? In Jump It, you always get rid of the squares to the left, so the board is obviously getting smaller. In this game, it doesn't look like you are removing squares from the board, right? And so that might give you pause, and you might say, well, I can't solve this recursively because the problem's not getting smaller every time, right? But it does, in fact, get smaller, right? So how does the board get smaller? Right? The idea is you never want to land on the same square twice, right? So the board does in fact get one square smaller every time, right? Because if you land back on the same square that you've already been on, you're going to stop the recursion immediately, right? So this board does in fact get smaller every time, which is nice. This means that there might be a recursive solution, right? We need some way to indicate that we've landed on a square before. So we're going to have to do something to deal with that. Okay, so again, whenever you're solving a recursive problem, sketch out small versions of the problem, right? Try to work out what your base cases are and your recursive cases, right? Usually when you're taught to solve recursion, most of the time you're taught to find the base cases first, but you don't have to do it that way, right? So here I'm going to find the recursive cases first, right? And so the idea here is I land on a square somewhere, it's got a value, right? I would like to know, can I move left starting from this square, right? So if you can move left, then you're going to move left and you're just going to try to solve the board starting at that next square, right? So that's your recursive call right there, right? I also need to know, can I move to the right when I'm on a square, right? If I can move to the right, I'm just going to move to the right and try to solve the board after moving to the right. And so that's your recursive call right there. Okay, so the version of the method that I'm going to write is the following. So it's called isSolvable. Right? It returns true if that board can be solved, and it returns false otherwise. Right? Now, it returns true if this board can be solved starting at that index. Right? It returns false if the board cannot be solved starting at that index. First time I call this method, I'm going to pass in 0 to indicate that I'm starting at the left-hand side of the board. Right? So I'm going to do the recursive cases first, right? The base cases we'll come back to and do them here. Right? Okay. All right, so I'm going to describe these 2 lines of code, and then we'll call it quits there. Right? So the first thing I'm going to do is I'm going to remember what is the value of the square that I'm currently on. Right, so the square that I'm currently on is that it has the index. Right, so I'm going to ask the board, what is the value that I'm currently on? Right. Now, I need some way to indicate I don't want to come back to this square again. So I'm going to change the board. Right, I'm going to set the current square that I'm on to the value -1. Right, and so this lets me detect later on, right, in one of the recursive calls, If I ever land on a square whose value is -1, I've been on this square before, right? And I can reject the solution at this point. Now, when you change the board here, right, notice that the method says this method never modifies the board. More accurately, it should say the method doesn't permanently modify the board, right? I'm going to change the board here, but later on down here, I'm going to undo the change, right? And so that'll let us satisfy the description of the method that says that the board never changes when you call this method, right? You don't want to change the board on the caller, right? Whoever called this method, they gave you their board. They're probably not expecting this method to change the board, right? They don't want that side effect. So when you're implementing this method, it would be nice if you did not permanently modify the board, right? Okay, so we'll see the rest of the solution in the next class, which I guess is on Friday? Friday, yeah.